And today's session will be taken care about by Ananya Pritilagna Biswal. So kindly, Ananya, can you please share your screen?
Yes. I hope it is visible.
Yes, yes, your slide is
Yes, yes, it's
visible.
visible.
Yes, please make it full screen.
Okay. So, good morning, everyone. I'm Ananya Pritilagna Biswal. Currently, I'm pursuing my PhD at National Institute of Technology, Rourkela, under the supervision of Professor Krishna Roy and Professor Arnav Ghosh. So, today I'm going to present my basically my research topic, that is AI/ML based controller designs and deployment on real time platforms. These are the some of the outlines which I'm going to discuss, beginning from overview, what objectives we have achieved, the overall system description to control various intelligent control architectures and how we controlling them with embedded system, modeling of system, how we model each elements in software as well as hardware, then the power flow management, the power management algorithm we have proposed, so to balance the generation side and demand side, and the results and discussion, the we have obtained some of the results, so we'll discuss about that, then the brief summary and the reference we have followed. So coming to the basic overview of the system, as we have seen today's scenario, there are the we are moving towards renewables because of the degradation of air quality. Now, as you can see, the daily air quality AQI is more than 400, so which is not worth living for human being. So that's why we are, it is safer side if we move towards the renewables as soon as possible. Not on these renewables not only available abundantly but also available free of cost. But their main disadvantage of this renewables, I can say, the intermittency, because solar may not be available in night, and the wind also may not be available 24/7. So it is better for to go for the hybridization of energy sources. For more reliable operation, like we can go for hybridization of more than one or two renewable sources. And this work is specifically developed for remote locations, like some villages or some rural areas, like hilly areas where the national grid may not be available. Till now, there is no electricity supply to some of these parts of our country. So this project aims to electricity supply the electricity to these rural areas. Here, for clean energy, solar wind, not only solar wind, but also biomass and pico hydro also we have considered. These are the control techniques, like we have implemented maximum power point tracking, and the battery controller is the main key point of this project, so that we can do the whole power management and pulse width modulation. The techniques are listed as like PI controllers. We are tuning with some meta heuristic algorithm, pulse width modulation, and some advanced control technique like sliding mode control. And here coming the artificial intelligence, what role it plays in this project for AI. I have considered the machine learning techniques to predict my temperature and wind speed in advance, so that if I can know the pattern, like which that my temperature increasing or decreasing, or the nature of wind speed, so that I can predict its value, so that I can make sure that the areas got supply 24/7 without any without any interruption. So these are some of the converters that we have incorporated, like boost converters, bidirectional DC-DC for our battery controller, and inverter to feed. It can feed AC load. We can, as well as we can feed to DC loads, and boost converter for extracting the maximum power from the PVs. So this I can say the overall system, that the advantages of these hybrid renewable energy storage systems, like with intelligent control technique, proper power management, so that we can balance the load demand with the generation. Continuous power supply, definitely it will help us for supply the power continuously and reliable. Obviously the reliability increases as we have incorporated more than two renewable energy sources, and losses will be reduced, so definitely the efficiency will be improved, and we can go for more than one or two renewable sources, and there is provision of adding also more number of sources, like in future if and there is shortage of this wattage of power, then we can go for another renewable sources. So these are the objectives to which we have achieved till date. Interfacing of various sources like solar, biomass, pico hydro, and to control with this various intelligent and advanced control technique, so that we can for seamless operation of these converters, and to reduce the losses as minimum as possible. And this because of this variable nature of this solar and wind biomass, this all depends on their availability. Like solar, its output power depends on its irradiation, and this biomass, how much dung we are feeding to the biomass. Or for hydro, it depends on the water flow or the water head, so they are completely dynamic in nature. So our main motto is to regulate our DC link voltage, so that it will be stabilized with the dynamic change in this all these parameters, like temperature or irradiation. And hence we will implement the energy management, which is based on our battery storage system, as this application meant for rural area. So battery is an essential part, so that we have considered battery as our storage element, and to manage the energy among the source and load. And it is also important for that not to overcharge or over discharge the battery. So simultaneously, by doing the energy management, we should maintain the charging and discharging cycles of the battery, so that our battery life cycle will also be improved. This is the basic system block diagram. Here, this is the biomass plant, and its output, as the biomass plant output is AC, we need to rectify it and feeding to the DC grid via a DC-DC converter. Similarly, for hydro, pico hydro, its output is also AC. We need to rectify it and feeding to the DC link via a DC-DC converter. And PV battery, they are the DC, so means their output is DC, so no need of rectification. We can directly fit to the DC grid through DC-DC converter. Battery will charge and discharge, means it's for its bidirectional power flow. We have considered a bidirectional DC-DC converter, and from this DC link, we are feeding to the domestic loads. This is the complete schematic. Like I have already demonstrated. Like this is the PV. We are installed a boost converter for this PV to for MPPT controller. We are extracting the PV power with this maximum power point control technique. And for battery, to manage the cycles, discharging and charging cycles, as well as for power management, we have installed a bidirectional DC-DC converter to ensure both charging and discharging operations. And here, these two sources are our biomass and PICO. We are rectifying this output using diode bridge rectifier. After this rectification, we are feeding through buck converters to the DC link. So to the DC link, we are installed all our four number of converters and controlling via their respective MPPT controllers. All the sources, we should ensure that all the sources should operate at their maximum power point. This is the control architecture. This is for PV. Like we are doing MPPT with BPV and IPV. The basic perturb and observe algorithm by generating duty, and through PWM we generating the switching pulse for the switch. And this is the overall control architecture for rest of this system. Like I have integrated all this control into a single diagram so that it will be convenient. And this is the whole power management scheme we are operating. Here first comes this is the DC link voltage. We are our main, as I told in objective, the main objective is to regulate this DC link voltage. So this DC link voltage is stabilized. Then for respective sources like for biomass, picohydro, PV, we are controlling with their corresponding current controllers and generating PWM and switching pulses uh, to the converters. So now I am explaining the overall control architecture briefly. Like here, we have designed all the hardware prototype with PCB board. As the capacity of PCB is not that much higher, we are operating with low voltage. Like in this case, we are maintaining the DC link voltage at 48 volt. So to this is the battery current controller. This whole block represented in purple. This is 48 volt, and we need to stabilize this DC link voltage. So via a PI controller. And this PI controller parameters like P and I coefficients, we are optimizing through this optimization technique that is represented as error minimization with generating ITAE. ITAE is our integral time absolute error. By integrating with our simulation time, we are generating this KP and KI values, means this optimized values. And after this is a dual loop control. This outer loop is generating the voltage. Then we are generating the reference current. This is IBB star. This is our reference battery current. And with this actual current, we are implementing the sliding mode control for generation of pulses to the bidirectional converters. And this block is for PV, like I have already told that this is for our MPPT controller. Similarly, for wind, we are also implementing this MPPT controller. And for feeding, we can feed both DC and AC loads through this system. So for DC load, we can directly feed, but for AC load, we need to invert. So we have also installed the inverter. So this is our dual loop inverter control by outer voltage loop, and again generating current. We are by this inner PI controller, we are generating switching pulses for these four switches using PWM. So this
Good,
controller,
good morning, madam. Madam, one doubt is there. That is the protection and safety purpose. You are not talking about this.
protection. Yeah, I will come while
Okay, okay,
demonstrating the hardware part. I will come to that. How we install means how we design the snubber and all. I'll brief about that.
okay.
So this is the inner control technique, like sliding mode control. The sliding mode design, first we should choose one reference that here in my case it is error signal, like I am generating the reference current for battery. As choosing after this error signal, we are defining a sliding surface that depends on our sliding equation. Like here in this case, I have this is my sliding surface S dot, which is represent lambda E dE by dt. Actually, this E dot is derivative of error and this error. Lambda is some positive values, and here this VDC reference, like outer loop control, then it is the inner loop battery current control. This is I have defined my sliding surface. So after defining sliding surface, then sliding design controller. So this controller is designed like U is the control input. Here I have designed. Yes. Anyone saying something?
No, no, you can mute her. You can mute her.
Okay. So this using this signum function, I have designed my controller, that is my control input U, based on this sliding surface, whether it is greater than 0 or less than 0. You can choose your own sliding control law, like greater than 1 or less than -1. So it totally depends on how you choosing your sliding surface. Then this is the generation of control input. Then system dynamics. For in my case, the system dynamics is this E integrate S equal to E integration of E dt. I am choosing the error. Then generation of this output duty cycle to trigger my switch of this bidirectional DC-DC converter. This is the elliptical path of this sliding mode control, that how it converges with respect to this is like plotted in x-axis. I have taken the error, and y-axis the derivative of this error. Then this is some of the modeling. I have considered the PV as single diode model, and the equations, corresponding equations are represented like I pH is the photocurrent, ID is the diode current, and I will be equal to I phase minus ID minus ISH. So this again I am representing this equation 1 in form of 2, like where the VT is the thermal module voltage, I phase will be defined by equation 4, and Vt is defined by equation 3, where T is the temperature, Rs is the module resistance, that is the series resistance, K Boltzmann's constant, Ns is how many number of cells have connected in series, IPS is the photocurrent, as I told, and I naught is the saturation, and A is the diode factor. Then for battery system, the battery system I have modeled using a control voltage source like this E with a internal resistance. So this is my B battery and I battery, which are and represented by this equation 1. So here is the no load voltage. Battery capacity will be defined by Q, and K is the polarization of this voltage. Then again, this equation 213 represents based on this battery charge equation, whether it is less than I reference current is less than 0 or it is more than greater than 0. Then coming to biomass and wind system, this biomass here in our campus itself, we have installed biomass. Its capacity is around 10 kilowatt, but we are operating at maximum 1 kilowatt. As I already told, I have designed all this circuit with PCB. So its capacity, if we increase, then it would be, it can't handle. So maximum we have gone up to 1 kilowatt. So this biomass plant, its basic modeling, like we are we are putting some dung, like some wooden, like what I can say, some wooden wastage or anything like that. So, and with a gas scrubber inside it and humidifier, they will generate the steam, like steam kind of, and that will generate electricity from itself. Inside there is a generator, so directly we can get the supply and operate our converter. So total gas yield will be defined by this equation 0.0036 into total dung availability, and this energy generated will be defined by this equation in total gas availability into CV into efficiency divided by 860. CV is the calorific values. And for wind system, we have considered a motor generator set, because as we can create here the real world wind turbine platform, so that we have considered a motor generator set. This is the mechanical power available, like P watt defined by equation 5. P watt will be equal to half rho A V Q. B is the wind speed, rho is the air density, and A will be the swept area of the turbine blade. Then this tip speed ratio lambda defined as equation 6. R defines the radius and W defines the turbine angular speed. And total for actual power we are getting is mentioned in equation 7. CP is our wind power coefficient, which depends on various constant values that we have chosen based on our requirement, like C1, C2, C3, C4, C5, and C6. And this, then coming to this pico hydro. Similarly, pico hydro also we have modeled by using a motor generator set. So that, but its actual model is like this: from river or forebay, we are keeping the water at a certain height, and by rotating the turbine by this water flow, we are generating the electricity. The main equation is the P equal to PPH, that is the pico hydropower, is defined by efficiency into G into Q into H. So this G is the acceleration of gravity, and Q will be the rate of power flow, and H is the efficient water head. And this Q again will be defined as BH, where B is the flow velocity, and B H at the breadth and height of means this height of this our this modeling, this system. So now coming to forecasting of temperature and wind speed of using AI. So for artificial intelligence, we have considered here machine learning. In future, we are also planning for deep learning. And in machine learning, three types like supervised, unsupervised, and reinforcement. So we have considered here the supervised machine learning technique. The process begins from data collection. Like I have utilized 60 years of data for training the model and 20 years for testing the model. And organization data, as the data we can get from NRA, like this government website, or also there's many free sources available like National Renewable Energy Limited, like that you can get the data. But they are giving us the raw data, like if you need hourly data or daily or monthly. So it depends on you how you organize the data. Then this model building, like I have considered four kind of model for my training purpose using this machine learning. Then results, analyzing the results, whether we are getting the least error or not. If we are not getting, then we can retrain the model. Then coming to data visualization, and as I told, if our results are not satisfactory, we can retrain the model and transform into visual results. This is the process followed, starting from training data, then using some machine learning model, that which model you are choosing, like random forest, support vector machine. That depends on you how what model you are using. Then after processing of the data, we are predicting the values, like for my case it is wind speed and temperature. Then correct output result. If we are getting the false result, we can retrain and this whole loop will be repeated. These are the um, comparison between actual and predicted values for temperature and wind speed. Like this here, this is for temperature and wind speed. This table represents the absolute mean error which I am getting. Like I have implemented four ML models like linear regression, decision tree, random forest, and support vector regression. So for wind speed, temperature prediction, I'm getting the minimum error using this support vector regression, which is 3.36. So it can also vary in your case, like what kind of data you are choosing, how, what is your model. So it will be based on your requirements. And similarly for wind speed, I'm getting the minimum error in case of linear regression like 1.96. I have also implemented all other models, but which value is you are getting minimum error, that I have considered the optimized values. Now coming to my optimization of my control parameters. I have chosen the PI controller at the output outer loop. Like for my voltage control, there I am optimizing my KP and KI value using some multiverse optimization. Actually, I have implemented using three algorithms like multiverse, whale optimization algorithm, and gray wolf optimization algorithm. All these three optimization algorithm I have considered. So the here I'm going to explain a little about this multiverse optimization. It's a concept. So this multiverse optimization is basically relies on like multiple universe, how they interact or collide each other. Like it's the Big Bang theory that causes a birth or destruction of a universe. So three main concepts like white hole, black hole, wormhole. This first figure is a white hole which can produce another universe, black hole that can absorb or destroy any other universe, and this wormhole, it basically works as a tunnel between this black hole and white hole. And the principle, like operating principle, is roulette wheel mechanism. This is the complete flow diagram. At the initial stage, we do the initialization process of these parameters like wormhole existence probability, TDR, that is traveling distance rate at the rate which the universes are traveling, and some random numbers also will initialize. Then after sorting all this universe, we'll find one normalized inflation rate for all the universe, and this fitness function of all universe will evaluate. Then I equal to the black hole index. We'll initialize I equal to 1. Then keep on updating this WEP and TDR. Similarly, again we need to update this white hole index, that is J. Then R1 we will select one random number, that is you can choose from 0 to 1. 0 to 1 is the best value for this algorithm. You can go for other values as well. Then for random number, we'll see whether this random number 1, this is the R1, whether it is less than our normalized inflation rate for EY, means for a particular universe. Then using this roulette wheel mechanism, we are equating whether this black hole index is equal to the white hole index or not. Then again we are, for more precise means value, we are taking another random number, that is the R2, and we'll check again this R2 is greater than less than our wormhole existence probability or not. Then we'll calculate this I of j, means this optimized universe. Then we'll increment j and check whether j is greater than the number of object or means universe. And similarly again for I, we'll check the similar case and we'll see whether we are getting the best universe or optimized results or not, and we'll follow the same process again till we find our optimized results. It depends on how many iterations you are running for. The more number of iterations, the more number of means precise data you can get. So these are these functions, like U is the universe represented by this matrix, and this equation is represented by Xij, and based on this normalized inflation rates. Xkj represents the jth parameter of kth universe. Similarly, xji, jth parameter of ith universe. And this random value, as I mentioned, that it is good to be between 0 to 1. And I inflation rate of UI means ith universe inflation rate it represents. This is our xij, the function values. like which depends on our traveling distance rate. We are considering two bounds, upper bound and lower bound. For more accurate, we are considering another random number, that is R4. And I'm taking two cases for this, like the random number 3 will be less than 0 or it will be greater than 0. So based on this two equation, the whole convergence process will repeat itself. Then this is the convergence curves I have got. As I told that three optimization algorithms I have implemented: fuel optimization, multiverse, and gray wolf. So these are the three curves for this all these this optimization algorithms. Here, this blue one is for the multiverse optimization, which convergence faster than the other two. Means I can say it is the for this case I have found this is the best uh, curve for my project, that is convergence faster within you can see like 10 to 20 iterations it convergence, whether this MBO and WA taking more time to converge. By by implementing the code, I have getting this KP and KI values, and for MBO, as I have seen this, my results are the optimized results. So this KP value is 2.92361 and KI equal to 51.9771. Although I'm getting approximately same, but based on my curves, I'm considering this is my best results for my control parameters.
Madam, sorry, madam. That is the madam,
Yes.
the optimize the value you are talking about, optimize the value. That is your duty cycle you have to optimize, or which parameter you have to optimize?
This KP and KI values, like outer loop I have told, I am comparing the voltage, means I need to maintain it at 48 volt. So for that I have implementing this PI controller. And this PI, KP and KI values, there are many ways now we can find this KP, KI values. But for my case, I have chosen this optimization algorithms. You can also do the MIMO modeling system, like multi-input, multi-output kind of matrix evaluation. That also you can do. But for my case, I have considered this algorithm optimization.
No, you are talking about DC to DC converter. So I have doubt the PV system, MPPT for PV system you are connecting, and you are using this algorithm. Then which
No,
parameter
no,
you have to optimize?
I'm not using this algorithm for PV system. I'm using
Okay,
for bidirectional DC-DC converter.
okay, okay.
Means that is connected to battery, and this battery controller is a dual loop control. So this outer loop part only I am considering this kpki values to optimize. So for that I have considered these algorithms.
Any limitation is there?
Yeah, it actually it's a time consuming process. You have to wait for 2-3 days so that it will get some means I have run till 250 iterations. For 250 iterations it took me around 3 days. So it is a bit time consuming.
Okay, okay. Because that all the algorithms, hybrid algorithms or individual algorithm will take some time to optimized. But specific limitation, anything is there? That's why I'm asking. Okay,
Um
okay.
Specific to what I can say, their control
Any that is
like
the any sensitive to population size or any tuning the parameters like this. I want to get the information this because the time
yeah.
consuming it is sure no problem because you have to run this algorithm. It will take some time, no doubt. That is the
Yes.
computational time will take time, no problem. But any specific that is the parameter is
Yeah,
required. This is the
actually it
limitation of this algorithm.
yes, yes. Actually, it depends on like which algorithm you have taken. Like previously, I was taking some PS algorithm, but some algorithms may be limited to local search, but not global search. So
Yeah,
it depends on algorithm. So you can do also hybridization like here I have considered three individual. You can hybridize like WAO and MBO to
Yeah,
get
you are not combining. That's why my question, because the hybrid is there means okay, but you're
yeah,
individually you are
because
considering.
yes,
Sir,
yes. If I
you can
found
have boundary
any
limits, sir. What madam want to
yeah,
say is boundary limits. You see, madam has mentioned upper boundary and lower boundary, no, sir. With that
Yeah, yeah,
boundary limits, she is getting that exact way of defining. When you
yeah,
change your
yeah,
boundary
yeah.
limits, it will be varying.
yeah, yes,
That
yes,
yeah. That is the manually you have to select the boundary limit, sir.
Yes, 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 yes,
Yeah,
yes.
yes.
yeah.
So that's
Okay.
why you can go for hybridization also. But for my case, I have defined, so I'm getting the values.
Yeah,
So
because
that
I thought that is the sensitive to the population size. It is the most limitation of this algorithm. That's why I'm thinking.
yeah, also you can define. It's actually total depends on you. How you what value you're choosing, how much iterations you are giving, what is the initial parameters. So it has many constraints. So based on
Okay,
that, you can.
okay, madam. Thank you, madam.
Thank you. So this is the basic model that is consist of this battery with bidirectional PV with boost and this pico hydro with buck converter and biomass with rectification, that is diode bridge rectifiers with buck converters. So this is the power management algorithm. So the we have defined the algorithm based on our SOC percentage. Like we need to take care of the battery as well. So we have considered the minimum SOC is 15% and the maximum SOC is 85%, so that our battery will not get charged or overcharged or over discharged. So we are defining this voltage values, and after sensing all these data like our temperature or speed or hydro output, we are sensing all this voltage and current data, and we are calculating whether how the power management is to be done. Like we have considered three modes of operation. So SPM, that is surplus power mode, LPM, lacking power mode, and BPM, that is balanced power mode. Surplus means if our generation exceeding the load demand, and lacking if it is less than, means generation is not able to supply the load completely, and balance means when our generation is equal to this lacking power mode. So we are defining this algorithm in two steps. Like first we'll see the rate of change of power, then voltage. If it is satisfied, then we will calculate our voltage parameter, like how much power it the source should generate, or how much the battery should supply, and will um, means, run this code again and again until we defining the modes of operations. Like these are some of my outputs I'm getting. Here in first case, I'm having this my PV power, this pink color waveform. This is my PV power. Here my DC and AC load both are uh, constant. Like my but and for each case I'm mentioning like three states: battery charging, battery discharging, and battery is idle. Where when battery is supplying no power, like you can see, this is the zero, means this output is zero, and battery charging means here it is negative, and discharging means here it is positive. Similarly for this case also, battery idle, battery charging, and battery discharging. And my DC load is same, this is the purple, and AC load is also the same. Here in second case I'm varying the DC load, DC load, and but AC load is remain constant. And here this PV power I'm varying from 300 to 200 and to 150. So this load is constant, but total load will be 550 watt. Then to satisfy this load, and for this battery is negative means it is consuming. To satisfy the load, my PV is supplying 300 and my wind is supplying 350. Similarly, for from 0.6 to 1 seconds, also this PV supplies 200 and my wind supplies 350. And for third, that is battery discharging case, PV is supplying 150 and wind is supplying, that is remain constant as 350. And coming to this case, this is my load varying case, this is my source varying case. Here I was varying this PV power and here I am varying this load power. So for this load power, I am varying from 500, 550, 500 and 400. So, and this AC load is constant, and my battery will be my battery will take care of this load demand based on my source availability. And my PV is supplying 380 watt. My wind is supplying 380 and my PV is supplying 220 watt. This pink one. So to satisfy this load of 550 plus 100, and my then PV is supplying 220, wind is 380, and my battery is supplying 50 watt. Similarly, from 0.6 to 1, my load will be 600, 5 plus 100, 600, and battery contribution is 0. So these supplying 220 plus 380. And after 1 second, my load demand decreases a little bit. So this PV is supplying 380 and battery also starts consuming by 100 watt. So my uh, wind is remain constant like 380 and PV will supply 220 watt. So these two cases I have shown here, and this is my DC link voltage. Its control. I have control these three techniques I have mentioned: PI, SMC, and PI SMC. That is the dual loop control. So for the better results I am getting for this hybridization like PI plus SMC, this curve I am getting without. Now it has less time to attains its maximum value.
Madam, one doubt, madam, please.
Yes.
Battery discharging and battery, that is the charging, you are not talking about SOC and SOH.
Yeah, actually, I have shown in the next slides. Here, I have not shown because I have considered two types of sources. Okay, here I have taken AC load with wind. In next case, I am coming where I have taken this biomass and hydro. There, I have taken only DC load. So I'll coming to the here I can show also this SOC percentage, but I have not shown. So it is, but with means while implementing, we have considered this SOC. Okay. Means this
SOH?
no SOH I have not done the results means the analysis, but SOC percentage I am taken care because if SOC is taken care of, definitely SOH will be fine. So into that much deeper battery operation I have not gone into, but SOC I have considered.
Okay. Now, how you are estimating the SOC? That's why I have doubt. That's
Estimating means I have fixed some, like I have told na SOC minimum and SOC maximum I have considered. Below
no.
this,
How you consider that is the you cannot blindly you cannot consider like this. how you are, as your experimental data, based on data, I am selecting this label and this label. That's why
Because yes, it can find, like you can consider 5% also you can consider. For my case, safer side, I have considered 15%. So
Oh,
there is no like bound, means
that is, that
limit
depends
that.
upon battery capacity. You are considering
Yes, yes,
15%.
yes, yes.
Okay, okay. That is SOH you are not considering, madam.
No, no, no. Because what I found that SOH will be definitely taken care of. Because if you are not overcharging or over discharging your battery, then its health will be regulated automatically.
Mhm. Mhm.
So now I have considered this two more sources I have considered, like biomass and pico hydro. Here I have presented my SOC. As you can see, the SOC percentage of SOC. So here my load is variation in load, means my load is increasing from 5 kilowatt to 5.5 kilowatt. The all the sources remain same, and this increase in load will be taken care of my storage, that is the battery, and this is the BDC, that is DC link voltage, which is stabilized, and this is the SOC while charging and discharging operation. Sorry, in this case, it is yes, discharging and charging operation. Then variation in PV power. Here, this my load is constant, my sources are constant. PV power varies, like from 1000 to 800, and again around 900. Similar, this surplus or amount of power generation will be taken care of this battery. Similarly, this is the DC voltage and this is the SOC. As here my battery is not supplying any power during after 1 seconds, so this battery SOC is almost constant. Like here I am varying both PV power and load power, and here load is varying in 3 steps, like at 1 5 seconds, 1 seconds. Similar, my source, these two sources I have kept constant, and this PV also varying, and this battery will take care of this remaining powers. This is my DC link voltage, and this is the SOC. Now, variation in pico and biomass. Till now, I have considered these two sources as constant. Now I am varying these two sources in a complementary way. Here my load is constant, my PV is constant, and this, if there is any fluctuation or change in load demand, that will be taken care of this battery. This DC link voltage is maintained, and this is my battery SOC. So now this is the specifications, like the ratings or controllers. Like we have chosen this DSP F28379D C2000 microcontrollers, voltage sensors, current sensors, IGBT models, that is one IGBT from Infineon, diode, driver circuit, core for inductor design, this bobbin, and heat sinks. All the specifications are mentioned. This is the complete header setup. Like we have wind battery, bidirectional, BDC, buck, inverter, this sensor circuit, this DC supply, RL load, and with our PC. This is our C2000 microcontroller. Then coming to C2000 controller, uh, I'm giving some brief ideas regarding that. I hope my screen is visible.
Yes.
So this is a real-time microcontroller of C2000 family. A brief idea I'm going to give that it consists of GPIO module, ADC and DAX, and EPWM. So this is basic working of this controller. Like from it can do sensing, control, processing like arithmetic operations and with interface. So it's we have chosen preferred because of high accurate sensing. Like it can choose sense up to 12 or 16 bit and up to 24 channels are available, and high resolution. Its clock frequency is 200 megahertz, and it can um, give up to 32 outputs. So it is most highly reliable controller with this high performance processing like floating point, and it can optimize control arithmetic instruction as well as like up to 925 MIPS. It can also be communicated through all this integrated communication like CAN, UART, SPI, I2C communication, etc. This is why we have chosen like we can see the plot like it has more than 600 MIPS with more flash size up to 1 MB. So this is where we stand. This TMS 320 F28 3790 microcontroller. Yeah, its clock frequency is 2 megahertz, and it's a 32-bit processor, floating point controller with trigonometric math input already installed within it. We can do any kind of arithmetic operations. Its memory like 51 KB, and or one another kind of like 172 KB of RAM. And this is the system peripherals like two kinds of external memory systems, dual 6-channel dual direct memory access controllers, 169 individual programmable, two CPU. It has two CPU and each has 14 peripheral units. These are some communication peripherals like USB debugging, as well as two control area network, high speed up to 50 megahertz it can produce, multi-channel serial ports for communication, serial communication. Like for my case also I have implemented in interface with MATLAB, like embedded system. You can also do by coding. It has its own software like CCS, where CCS Code Composer Studio or C2012. So I have done using the interface with my MATLAB so that I can generate the EPWM pins through this controller and feed to my converters. These are some of the subsystems like four ADCs and one simple and hold on each ADC. 16, it can operate in both modes like 16-bit mode or 12-bit mode. So these are some of enhanced control parameter like 24 pulse width modulation channels, high resolution pulse width modulation channels. That is deadband support. Deadband support is like when we operate inverter, we need some time gap between on and off of the first leg to the second leg, or otherwise the whole converter will be short circuit. That comes the concept of deadband. And six ECAP modules, enhance three enhanced quadrature encoder pulse. All these features. This is how it looks. This is the C2000 control launchpad. Here, these are the GPIO pins. These are the EPWM pins. There are USB cable. It can we can supply it three. It can support up to 3 volts. This is the main processor. This is the CPU of this controllers. These are the jumper pins. All these jumper pins are like this is the ADC, J21 is the ADC, 1920 are the optional SMA pins. So these are all this pin configuration of this Texas built C2000 controller. This is this manual. It comes with this manual so that we can distinguish which are the ADC pins, DAC pins, or EPWM channels. According to based on our requirements, which pins we want to access. These are the pin configuration, and these are the corresponding GPIOs or ADCs. Here it is EPWMs. For our pulse generations, we need to access these EPWM pins. Similarly, it continue. These are on-chip modules. What it consists of? As I told, GPIO modules, that is general purpose input output timer modules, EPWM, inbuilt ADCs and DACs, QEP modules, memory, and communication peripherals. The GPIO modules, these are multiplexed kind of modules like input, whether we can use it as input or as well as output. So 169 EPIO modules. In each port, 16 bits are accessed through MUX. So that is port A, that is consist of 32, port B, till port E there are 32 pins, and port F that consists of 9 pins. These are now coming to MATLAB interfacing. Here, with MATLAB interfacing, we are getting this pulse generation. This is a CRO picture I have inserted. This is my pulse I'm generating with with this interfacing of MATLAB. So any kind of waveforms like sawtooth generator, we can also generate using this C2000 controller. This here also EPWM, with this EPWM channels, we can use like our SPWM here, how we implement in MATLAB also, here we can also implement. This is its internal architecture, like clock, compare registers, it compare logic, some time-based counter also. It has action qualifier with deadband, period register, EPWM chopper, trip zone, with some digital compare circuits. Here, this TPWM is calculated as this formula. This is TB pair D plus 1 into TB clock. This TB clock is the time span with one step, like it goes from 0 to 1. This is if we choose up counter in our controller, and this is how we get the pulses if we choose the down counter. This is the TBCTL, this is TBPWM, and this is the TBPRD. And obviously our function will be 1 by TPWM. This is if we choose both up and down counter. The formula will be, there will be a little bit change in this formula. So based on that, we can calculate. This is the system clock. System clock frequency is 200 megahertz. And HSPC clock, that is we have chosen according to it, based on your requirement. You can choose your clock division and HSPC clock. This is our action qualifier. So first 15 to 12 bit are reserved. After that, we are comparing our counter and we are generating our pulse. Like 00 means do nothing, 01 clear, 10 set, 11 toggle. Based on this, it will generate our pulse. How means what command will give? Based on that, it will generate our like triangular, sawtooth, or whatever we require. Like here, this is EPWM-A and this is EPWM-B. These are some of the pictures of these converters. Again, this is some references. That is a Texas Instruments product. So you can find more about at their website. This is laboratory section. This is the first lab section. Here I am explaining the pulse generation of a single converter. Later I will show for the whole microgrid system.
Excuse me, we can't hear.
Okay, I am explaining. You just see the video. See, this is the buck converter, input supply, this is output supply, DC power supply. Here my input is coming. Here my output, input capacitor. As input side, this is there is no need of means higher capacitor value. So this is a small capacitor, and this is my output capacitor, and this is a my IGBT installed with its heat sink for protection. This is snubber. Someone was asking about protection, I think. This is the snubber. Means to protect the switch from any dv by dt surge, like instant spike. There should be instant spike. So we have connected this snubber. You can there is various literatures you can find for snubber design, how to design the snubber to protect your switch. And this is the heat sink. CR, as I already described, CR101A. This is the specification of this heat sink. So this is my complete switch and its protection. This is my inductor. This is a ETD core, and this white wire is the leach wire, which is very means it can protect from us any leakage current, and it is insulated outside. This is leach wire and this is my ETD core. We have designed inductor based on our required value. This is a 24 pin bobbin, and we have designed it for around 25 kilohertz, and this value is around 700 to 800 microhenry. This is output capacitance. It is large because there will be ripples at the output side. and this output is connected to this resistive load. Around 300 ohm rheostat we have connected. This is the driver circuit. This is the driver chip. The specification I already mentioned. This is a converter circuit. This is whole driver circuit is controlled through this C2000 microcontroller, and this driver, from this driver I am feeding gate pulses. As you can see, these three colorful wires I have connected through to my switch, that is IGBT, to provide this gate supply. This is a SMPS. From this, we are giving supply to the driver, that is plus 5 volt. See, this is my MATLAB to C2000 embedded, means interfacing. I have interface this. This is the EPWM block. Here from EPWM5, I am giving pulse, and this is the pin number 70. I have described the
Excuse
pin
me, madam.
numbers.
Hello, can I ask one question?
Yes.
So, for your components, when you are touching, does it require ESD, electrostatic discharge? Usually, we wear like a
Yeah,
wristband.
sometimes we get socks. Yeah, yeah.
Okay. Okay,
But
thank you.
it is kind of protected, means this controller. But from our converter, sometimes we get this leakage current.
Yeah, maybe particularly when you are touching IC pins. Otherwise, if the PCB is coated with something else, then there should not be an issue. Okay,
Yeah,
maybe
yeah.
all ICs may not require that much ESD. That depends maybe on your room environment.
Yes, yes.
Thank you.
Okay. Now I'm giving supply. So you can see the pulses. These are the pulses I'm getting from this C2000 controller. This I'm generating a pulse of 25 kilohertz with point 4, I think. 0.6 duty ratio. After generating the pulse, we are feeding. Now I am switching on the supply. This I have 10 volt supply I am giving. we are getting the pulse. We'll measure the output voltage now. So this is a buck converter with 0.6 duty. I'm getting around 6.62 volts. So this I have explained for this single converter working. Similarly, I'm uh, going back to share my screen and demonstrate about the whole uh, laboratory session. I hope my screen is visible.
Yes.
So this is my overall laboratory session. So this is a like complete my microgrid setup consists of all these sources PB, biomass and picohydro. This is the C2000 microcontroller. This is the whole microgrid setup and I'm controlling with this embedded system like I'm feeding the pulses through this MATLAB and C2000 interface. These are the 4 converters like buck. These are 2 buck, boost and bidirectional. This is PB, this is battery. This is the battery. Two buck are for biomass and picohydro system. These two sources, from these two sources, I am giving supply to my drivers circuits. And we have installed this biomass plant outside our department. Similarly, PV on rooftop. And for picohydro, I have taken this motor generator set. This is my driver circuit. There to feed the driver pulses, means switching pulses to all these 4 converters. This is my sensor board. It consists of various voltage sensors and current sensors. I have already mentioned its specifications. This is the inductor board designed for each of this converter. I have kept all the inductor in a single board for more convenient. Now I'm going to explain each individual part. This is the buck converter. This is the switch with heat sink. This is another buck converter. Heat sink, diode, input capacitor, output and input. This is the snubber circuit. As this hydro and biomass are AC, so after rectification, we are feeding to the DC-DC converters. This is the boost converter for PV. This is IGBT. This is input capacitor, output capacitor with snubber and this diode. This is the bidirectional DC-DC converter. As this project is meant for rural electrification, so battery is the necessary part. So to control this battery, we have installed this bidirectional DC-DC converter with two switches, this capacitor and this is input and output. This is the input and this is the output. This is the battery. From this sensor board, I am sensing the voltage and current data which are required to control through this ADC channels to this controller. There are PWM channels for supplying these gate pulses. From there, I am supplying gate pulses to these 5 driver boards. All these drivers and converter circuits we have designed using Altium software. And so all these converter schematics we have designed and did in our lab. This is the chip, driver chip, that is a Infineon chip. Specification already mentioned. This is the inductor boards for inductors designed for each converters. This is the sensor board. These are voltage sensors. These are the current sensors. This is the resistive load. With respect to any fluctuation, how we can regulate this output load voltage, means to stabilize this load voltage. We are controlling this load voltage through this sensor board and this C2000 controller. This is the complete embedded system control. Like I have interfaced MATLAB with the C2000. This is how the interface looks like. These are the EPWM blocks. I am generating duty cycles from these EPWMs. You can also go for coding, with C embedded C coding. Here I have implemented directly from MATLAB. This pulses from this controller to driver boards, then from driver boards to these converters. This our biomass and hydro, their capacity is around 10 kilowatt, but we are operating, means for my case, I have operated up to 1 kilowatt. As in previous session, my colleagues Jaydev and Riju had also demonstrated about their project. They have gone up to 5 kilowatt. And the operating frequency, I'm operating 20 to 30 kilohertz. This is the rheostat, that is, you have considered this as resistive load. We can also implement with Harrell load, and we also did, but here we have shown only for resistive load. For power management, we are doing this among these sources and this load, how the load demand is should be satisfied. And I have all shown various mode of operation and this experimental results. I am going to describe now. So these are the experimental results, I have considered two cases. Like here, my DC load change, and here my load is constant, but my PV power is changing. So DC load is changing 400 to 450, then again 400. Wind is constant, PV is constant. The remaining power will be taken care of my battery. Similarly, here DC is constant at 400, wind is at constant at 300, PV is varying from 300 to 250 to again 300. This battery PV is the battery power that is taking care of my source fluctuation to satisfy my load demand. This is my DC link voltage, and here my AC load. I have considered the AC load, but as the CRO is 4 channel, I have shown it into in a different window. So this is brief summary. Boost converter is controlled with MPPT control. PI implemented successfully with a dual loop control like PI plus SMC. DC voltage is maintained irrespective of any change like wind speed or irradiation or load. The optimization results for PI tuning is done using various nature-inspired algorithms. Uninterrupted power supply is also ensured, and proper power management algorithm also implemented for the energy storage system using bidirectional DC-DC converter. And temperature and wind speed forecasting is also done using various supervised machine learning techniques. So these are the references. I have followed some of these references. So thank you. You can reach us at this. This is my mail ID. So I hope this session will be fruitful for you and you can gain some insights from this. Any queries?
Is there any queries? Please let us know.
Madam,
Yes.
Madam, for sliding mode control, you have used a control law U equal to half into 1 minus signum of L. This will
Yes.
introduce lot of chattering. I think you have to
Yeah.
go for other methods like ERL or ERL.
Yeah.
Okay. So you
Yes,
have used.
for chattering, you can optimize the SMC itself, or you can like introduce another control also. Means you can change the parameters also, like SMC parameters. So anyway, you can do it.
Okay. For Madam, for wind system, have you ensured MBPT? Means-
After this rectification, I have considered this voltage and current, and I have feeding the values with this perturb and observe algorithm and generating the duty.
Okay. Thank you, Madam. Okay.
Thank you.
Ma'am, I'm having one question.
Yes.
How do we calculate the efficiency of the overall system?
Actually, from hardware part, we have sent the powers. From that, we have just a rough estimate. I can't say I did the whole mathematical analysis, but from the
Okay.
simulation as well as the experimental results, we did a rough estimate.
Okay, means what is the mathematical equation by which we can calculate? Because through
Uh,
closed loop, we are maintaining the output voltage constant. Then power also is maintained constant as per our design.
Power, no, I haven't considered constant power. Means I have shown various cases.
Okay.
I have shown one case of varying DC load or varying AC, varying source power. So power will vary, but
Okay.
we have to maintain the DC link voltage anyhow. Otherwise, how can we feed to the domestic loads? There will be voltage fluctuation, na? So we need to maintain that voltage.
Okay. Okay. Thank you, ma'am.
Thank
Hello, madam, can I ask one question?
Yes.
Just for a moment, or we can do one thing, that efficiency normally we are going to calculate. Suppose you are having a load, okay, so connected to your DC bus, so you can calculate the load current and voltage, okay. Then
Okay.
from there basically we can do the resistive kind of load, okay. So
Okay.
voltage and current if you able to get, so you can easily find out that output power. Now I am coming to the input side. Suppose you are having a
Okay.
individual source, so source wise you can individually, in not this case, I think yesterday when they have plotted, when another lab session was there, you can see that individually current and voltage for individual sources also been calculated, okay. So
Yeah.
calculated
In the
means you
open
can
loop, sir.
also, yes,
Open
I'm
loop
talking about now
hardware. Okay.
open loop. Yes, I'm talking about now
Yes.
open loop. Just crude method. I'm
Okay.
telling you how crude method you
Okay.
can able to check the overall thing. Suppose if you are having a two sources, okay, as well as battery, you also take in your consideration. So if all of you add and then you can go for that ratio output by input, then you can make it percentage. You will get somehow a rough estimation. You can able to get it, and by that
Yes.
way you are
Yes.
Yes.
doing the same way to this is a very crude method, but I think we can go with that idea. We are also estimating like that
Okay.
way also. Okay, ma'am.
Okay,
Yeah. Okay.
and
Thank you, sir. Thank you.
one
Thank
more
you.
point. Yeah, yeah. As sir told, I want to add, like for closed
Okay.
loop, you are asking. Here I have shown my sensor boards. So, like from this sensor data, also we can get the means actual values. So from
Okay.
there we can go. And if you want to go for more detailed calculation, then we need to refer the specifications. Like the IGBTs
Okay.
I have chosen, the inductor core I have chosen. From there
Okay.
data sheets we can calculate the actual losses what is occurring.
Okay. And efficiency have to be in what range normally
If
for
generally
this
DC-DC converter offers higher efficiency,
Uh,
like more than
multi-input
90%.
multi-input
huh.
systems for this
Yes,
microgrid
actually,
systems?
madam, she is talking about individual converter, but I can tell you for overall efficiency, it will come in the range of 92% to it can vary up to, you can see 96% like that, it is varying. Okay, we have
Varying.
Yes,
observed.
Okay.
yes.
And if you
Yes.
increase the power level, the beauty of that observation is that if we increase the power level, the efficiency also going to be increased. That we have,
Increase.
we did some of the case studies. From there we can able to observe all those things, and the modeling that Ananya is telling, that for the modeling and all those things, so switching modeling, ideal cases and loss calculation from the data sheet, so you can accurate losses, you can also be nearby
Okay.
losses you can also be calculated, okay.
Calculate.
Okay.
Huh.
Thank you, sir.
Yes.
Thank you so much.
Okay.
Okay.
Huh.
Hello.
Yes.
Okay. In our case, we have multiple sources are there. Different types of sources are there. So
Okay.
how the load sharing is happened? Suppose there is a sudden load demand or sudden load change from the load side.
Okay. Basically for this sudden change in load, there is storage system. If your sources are enough to generate, it's fine. Otherwise, you must have some backup system. Or the for sudden change in load, I can suggest supercapacitor because that is high energy density. So you can, if you install supercapacitor also, you can tackle the sudden increase in load demand.
In this work, you implemented any such load sharing algorithm or something?
This power management algorithm I have explained. Na, this I have considered different cases like change in AC load, change in DC load, or change in my PV power. So these cases I have considered, like various modes of operation I have considered.
What about the response time? That is also taken into account. Means some sources will respond at a
Yeah,
faster
very
rate to the change.
very first means like from the results you can see it like here if my load it changes, this battery is responding immediately. Means it's very fast, like immediately.
Okay, okay.
Hello, madam. Can I ask one question?
Yes, yes.
Yeah, so yeah, for fast response in the battery technology, for throughput, high throughput current, you're using some lead acid or any lithium side or any other technologies here?
No, I'm using the basic conventional lead acid.
Lead acid. Okay.
Yeah.
So on battery technology side, you're doing any research happening in your university in NIT Rourkela?
Yeah. And some one of my senior is doing with this battery SOC and state of health estimation.
Means like on other technologies like liquid sodium or any on the lithium side. Particularly
So
these days, liquid
actually
sodium
the
is coming.
details I can't say, but you can refer to his papers like
Okay.
Saurav. So you can refer to his papers. I can't say
Okay.
means properly because I am not into that field. So
Okay, no problem. Thank you.
okay. Yeah.
Okay, is there any other query? So we can going to conclude it. Uh, any other queries from the esteemed participant? Okay, so I think there is no other queries. So thank you, Ananya, for giving your very good presentation and discussing all the computational as well as experimental point of views and its designing driver circuit is designing of the driver circuit, total overall working. Okay, so I hope our participants can understand a lot of things from your studies. Okay, so we hope that that session is useful from their end also. So thank you for giving your time to us. Okay, thank you, Anunya.
Thank you, sir. Thank you.
Thank you. Okay, so we can go to our next session. Okay, so next session is scheduled from 11.